Good morning. Um, we are ready to move on with chapter 31. This is actually our last lecture for the semester. So all we've got ahead of us now are the midterm and the finals. So we want to make sure that we are well prepared for that. So in the last lecture, we had been looking at, we said electromagnetic fields propagated by accelerating charges, generated by accelerating charges, and these electromagnetic fields would then propagate over long distance. So now we want to look at some of the energy equations that we've already kind of set these up. We've been looking at some of these over the course of the semester. We want to bring them back. So if we're looking at electromagnetic fields in general, the electromagnetic fields have energy densities associated with the electric field components, and then energy densities associated with the magnetic field components. To get the total energy density, the energy per volume, what we can do is add together the contributions from the electric field components along with the contribution from the magnetic field components. So each of these contributes half of the energy. Now, the way that the textbook is using the notation here, what they are doing for the energy densities, they're writing the electric field energy density 1/2 epsilon naught times E squared, and the magnetic field energy density 1/2 B squared over mu naught. Now they're using their epsilon naughts and their mu naughts, and I guess that's okay. And you guys are welcome to use these too, but we're going to go through kind of their equations that they have, and then we'll look at a set of equations the way we've been looking at them, the way I've been presenting them at least, and we'll see how that compares, and you can use whichever approach you want. But these are the energy density formulas. Now, when we have these electromagnetic propagating fields, the electromagnetic waves that we're talking about, we said that if they're the acceleration fields, then they could travel long distance and they're going to carry a certain amount of energy with them. So they can carry energy far, far away from the charges. Kind of like the antenna example that we looked at, KQED, going to radiate a radio signal, and that energy is just going to travel long, long distance. Your cell phone, right? Your cell phone transmits a signal to a cell tower, and that takes that signal and directs it to other cell towers, to somebody else's phone. So anyway, here's the energy being transported by, oh no, not the wave. Okay, I got to cross that out. We'll just call it the energy being transported via electromagnetic fields. So this is what it looks like. Now they're setting up something probably more complicated than what we need, so I'm not going to worry about it. I'm just going to say this: since the profile of these fields are propagating at the speed of light, then there's going to be a certain amount of energy. Wherever there's an electric or a magnetic field, there's going to be a certain amount of energy associated with those fields, and as the field propagates, the energy gets carried along. If we think of this as a series of photons, right? So if these electromagnetic fields are a bunch of photons that have been radiated by these accelerating charges, then that energy is going to be carried by the photons, and they're going to be absorbed at some later time at some other location. And then the energy gets transferred. You know, like the sun shines, a bunch of photons get generated in the outer layers of the sun. Those get packaged, sent through space towards planet Earth, and the energy gets transferred here. So you can transfer energy long distance using these electromagnetic fields. All right, here's some other notation they're using. Now, a couple of warnings here. They are talking about intensity. So what they're saying is that the intensity of the electromagnetic field is given by 1 over the area times the power. So this is the power, this is the area, this is the intensity. Again, I'm going to come back and go back through this, and I hope find something that, to me at least, feels more like just some kind of random equations that we have set up here. Something that has a little more consistency to it. When we look at the intensity, we want to be looking at an average value. So if I do have electromagnetic fields like the ones we've looked at, where the electric field and the magnetic field vary from one location to the next, there are going to be regions along which the energy density is higher. So we want to average over that in order to determine what the average intensity is, and to be able to calculate how much energy we will successfully transfer. Okay, here's my preferred way of thinking about this. So this is like energy transfer through electromagnetic fields. The fields that we're going to have are E and B, and I want to be working in terms of C times B. I think that's going to be important for us, that we think in those terms. So these are the acceleration fields that we have, and since they're acceleration fields, fields generated by accelerating charges, the magnitude of the electric field and the magnitude of the magnetic field multiplied by C, those are going to be the same. So E equals CB. Let's see, I think I put some numbers in here. So to get started, what I said was, let's imagine we have an electric field that is on average, so these are RMS values, kind of the average RMS value of the electric field is 60 newtons per coulomb. Well, if it's an acceleration, field, if it's radiating, then C times B would also be 60 newtons per coulomb. That's how this works with the acceleration fields. Now, in parentheses down there, I put, okay, what would it be in Tesla? And in terms of Tesla, that would be 20 microtesla. So to switch out of newtons per coulomb and back into Tesla, I just divide through by C to get that value. All right, so that's the field values that we have. Now, our energy density formulas that we've been working from, and I guess this one, chapter 24 maybe, and here maybe chapter 30, where these were first introduced, and I can use those. So this is the energy density associated with the electric field. This is the energy density associated with the magnetic field. To get the total energy density, I can add those together. Now that's just a formula. I can plug the numbers in and find out what it is. The E field and B field values are here. And the little k is the electromagnetic force constant. So that's 9 times 10 to the ninth, or 8.99 times 10 to the ninth. And when I did that, what I ended up with as an energy density was 15.9 nanojoules, where nano is 10 to the minus ninth. So not much, right? And that's nanojoules per cubic meter. So if I've got an electromagnetic field that's propagating off in this direction, and I take an entire cubic meter of it and ask how much energy is stored in a cubic meter of that propagating electromagnetic field, it's 15.9 nanojoules, 10 to the minus 9. That's pretty tiny. Now, it's not a very high energy density. Oh, let me step back there too. So it's that much in the electric field components, and then I get 15.9 in the magnetic field components, so it actually is kind of double. The combined energy density, 31.8, still kind of disappointing. There's not a lot of energy stored, at least with this strength of the field that we've put in. Now to get intensity, intensity is given by U times C. So intensity, if you remember, the units on an intensity are watts per square meter. Now what the textbook is using is they're calling intensity the Poynting vector, and they're using the symbol S, at least in chapter 31. When you guys pick up again in chapter 32 in Physics 4C, they're going to start calling the intensity I. So for one chapter, they call intensity capital S, and then for the rest of the, that's the exception. All the other chapters where intensity comes up, intensity we use the symbol I. I'm going to go ahead and just use the symbol I for this. And so the intensity is U times C. And again, just plugging in numbers, that gives me 9.54 watts per square meter. So not a hugely intense signal, but you know, those are the numbers that we came up with for our energy transfer example. Now, if I take a look at just how much energy is being radiated by a charge undergoing an acceleration. Now this derivation is a little involved, and it's not something I would expect you guys to do on a midterm or on a final exam, but it is kind of interesting to step through and see how this works, and we can learn something along the way as far as how the intensity is mapped out. So let's see, we've said that for a single accelerating charge, there's an electric field, there's a magnetic field, kq over r, a over c squared sine theta. So that says, look, the electric field is 0, and the magnetic field is 0 directly out ahead, but as we increase theta, the most energetic, or the highest values for the field, are directed at 90 degrees. So most of the field strength is out to the side of that charge as it accelerates. So it's mostly, the effect we're seeing with radiation is going to be mostly to the side. Now I can take those field equations and I can, from those, solve energy density equations. So I'm just using the formulas that we had introduced. And here is the energy density for the electric field components. Here is the energy density for the magnetic field components. Here is a spurious line. I don't know what that's doing. You can cross that out. And when I added together the energy densities for the electric and the magnetic field, what I got was this energy density. And what I'm seeing as far as the energy density is it drops off like 1 over r squared. Okay. So as I move away from that charge and get farther and farther away, the energy spreads out. And it turns out that I have energy densities then that drop off like r squared. Now there's the angular factor too, so it's saying again, it's the 90 degree direction, that's where the highest intensities are going to take place. All right, so what we can do then is to take the energy density, multiply by c, that will give me an intensity. And so that's my intensity formula, and I boxed it, and I'm proud of that formula. And again, I'm seeing that the intensity of light, the intensity of the electromagnetic field, radiating away from this accelerating charge, the intensity varies like sine squared theta, and it varies like r squared. Okay, so and there is our statement right there, and this diagram was meant to show that the intensity is bigger here, and I don't know if I drew that the right way or not. Anyway, stare at the mathematics. That'll tell you how this works. That's kind of the standard pattern. Now, what we can do then is this. We can say, all right, here's the charge. It's accelerating. We now have an intensity formula. How could we add together all of the intensity to calculate the power, the total power radiated by an accelerating charge? As the charge accelerates, it radiates light. What's the total power going to be? We know what the intensity is as a function of angle. But let's go in and see if we can calculate the integrated effect. And we are going to need to do an integration here. So what we can say is this. We can take a sphere and we can break it up into a series of circular rings. So I can think of the surface area of this sphere as a series of circular rings, and along each one of those circular rings, I know that there's going to be an intensity, and the intensity, I got to kind of switch back and forth between pages. I didn't rewrite this. So that's the intensity formula. That's what I want to keep staring at. Now, when I carry out the integration, r is actually not a variable. We just pick a distance r, and it doesn't, we're not integrating over r. We're integrating over one spherical shell at a particular value of r, so that's a constant. Now, the sine theta factor, that is going to have to get integrated, because what that's saying is when I start looking at, so remember that sine theta factor, I kind of tacked it on the end right here in the integration. And what that's saying is when I start with the ring right at the front, that's not going to have much intensity because the angle's really small. And then as I move from this ring to this ring to this ring, when I get to the ring in the middle, that's going to be the one that has the highest intensity, and that's going to integrate out to be the largest contributor to the overall power output. Now, just to check my D area formula. So I wanted to check how do I carry out this integration of a surface area of a sphere. So I wrote surface area of a sphere. And what it seems like is, see that circular ring on my spherical sphere? That's going to have an area that's equal to, well, it's going to be the circumference all the way around. Now, the circumference of a circle is 2 pi r, but not all of these rings have the same, in fact, all the rings have different values of r to them. R is the distance from the center out to here, but what I want is the r value of the ring, and so it's this distance. And if this is r and that's theta, then this distance is r sine theta. So the radius I want to use for each of those circular rings is r sine theta, and the rings are going to be smaller at the front, they're going to get bigger in the middle, and then they're going to get smaller again at the back. The sine theta factor is going to be keeping track of that for us. Okay, that's the plan here, so we'll see how that works. So let's see, that's the circumference then, all the way around a ring. Now, the other perpendicular direction that I have to consider is that direction right there. That distance along that short segment, kind of the thickness of that ring, and what that's going to correspond to is r d theta. So theta is equal to 0 right here, right? And then as I integrate, theta is going to increase. And you know, when theta gets to some particular value, the thickness of that ring is going to be r times d theta. So I'm hoping you guys have seen this in your calculus classes. If not, ask your instructors. Hey, when are we going to see something like spherical coordinates and calculating surface areas of spheres? Anyway, so this is how much area I have in each one of those strips along the surface of my sphere. And now what we can do to calculate the total area is integrate all of this. And so I'm going to integrate that. Now, a factor of 2 pi comes out. We said r is actually a constant. R isn't changing. R is the radius of the sphere. So for now, for the purposes of calculating my surface area, r is a fixed constant. And so the r's also come out. What that's going to leave me with, though, is going to leave me a factor of sine theta, and it's going to leave me a factor of d theta. And so sine theta d theta is going to get integrated between 0 and pi. Now, the reason it's 0 to pi, not 2 pi, is because by the time I've integrated from theta equals 0 out to theta equals pi, I have included all the rings. So all of these circular rings, these infinitesimal rings that make up the surface area of my sphere, by the time I get to pi, I've counted all of them. If I come all the way back to 2 pi, I'll double count. I don't want to double count the surface area of the sphere. So the idea is integrating then from 0 to pi, and the function we're integrating is sine theta d theta, and if I integrate that, integrating sine theta d theta gives me the cosine of theta, and actually it gives me the negative cosine. But what I'll do to get rid of the minus sign is take the limits of integration and switch them. We've done that several times now. It is one of my favorite tricks to avoid minus signs. So I'm going to be evaluating the cosine of theta between 0 and pi. Now at 0, the cosine of theta is going to be 1, and at pi, the cosine is going to be negative 1. So that says, carrying out this integration, evaluating the cosine function at the limit, 1 minus a minus 1, that's a factor of 2. And so the surface area of a sphere, I am predicting to be 4 pi r squared. So it seems plausible. In fact, it seems right. It seems like we have got the correct form for D area. The D area that we've defined seems like it's working. So let's try this out with what we want to do now is use that very same dA that we've defined, and we want to come back and determine the total power radiated by our accelerating charge. Okay. So again, now we're going to come back with this intensity formula. So let's stare at that a little bit, and then move on to this integration right here. So now, instead of using a D area, what we're going to be integrating is D power. So we want to take each one of these areas and multiply it by the intensity. Well, we said that each of the D areas is a function of theta. Here's sine theta, and here's a factor of d theta. Well, the intensity of the light of the electromagnetic fields being radiated in that direction theta, that's also a function of theta. So in the integration, I'm going to have two factors of sine theta, and those are coming in because of my intensity function. And then I'm also going to have a factor of sine theta and d theta from the definition of the surface area infinitesimal expression, the expression for dA. All right, let's try this. So I'm going to take that intensity formula, and the intensity formula was like 1 over 4 pi kq squared a squared over c to the third power. Now it had a factor of 1 over r squared in it. It said that the intensity is going to drop off like 1 over r squared, and we said, well, that's kind of like as you get farther and farther away, the intensity of the field is going to drop off, so the energies will drop off as well. Now, when I look at the integration over that surface area, what I'm picking up is 2 pi r sine theta r d theta. So I am on the d area is picking up 2 factors of r squared. So what's going to happen here is when I start collecting terms, let's see, kind of jump ahead and see what the next step might look like. When I start collecting terms, the 2 pi from the d area is going to cancel mostly with the 4 pi. That's going to leave me a factor of 1/2. Now all of these constants stay around, k, q squared, a squared, c to the third power. So I've got the 1/2 k q squared a squared c to the third power, but notice what happens is the intensity is dropping off like r squared, but the surface areas are getting bigger than like r squared, and those two effects cancel. So this is a big deal. What it says is, look, the power is not a function of distance. So if we think of it this way, let's take a spherical shell and surround this charge as it accelerates. If I add together all the energy being radiated through this spherical shell, well, when I get out to this spherical shell, I'm still going to have just as much energy. And when I get out to the next spherical shell, that will also have, the power is not dropping off. And what that says is there's a consistent flow of energy away from the charge. So when I have a charge that's accelerating, it's going to radiate light, there's going to be a consistent flow of energy, and that energy, it's not coming back. So the charge is radiating away energy. Now, could we do the same thing with the velocity field? So this is specifically the acceleration fields that we're taking a look at here. What if it was the velocity fields instead? If it were the velocity fields, would we have a consistent flow of energy away from a charge that's moving at a constant velocity? And what we saw with the velocity fields is that the energy densities dropped off like 1 over r to the 4th, not r squared. So if I were carrying out the same integration, but using, instead of the using the acceleration field formulas, I was using the velocity field formulas, what we would find is, as we go from one shell to the next, the amount of power is decreasing. So I'm not getting a consistent transfer of energy away from that charge. So velocity fields can act at a distance, but they don't actually consistently they don't radiate energy away just as a result of their velocity. But acceleration charges do. Just by the mere fact that they're accelerating, they are going to be radiating light. Whether or not that light is going to be picked up by another object in the near future. Okay, so that's an important distinction between the velocity fields and the acceleration fields. And that's why in chapter 31, when they start talking about electromagnetic fields that are propagating long distance, that's why we're exclusively, in this chapter, we've stopped looking at the velocity fields, we're only looking at the acceleration fields. Those are the ones that are responsible for these long distance transfers of energy. Okay? All right, and I know I keep repeating that, but I always feel like it doesn't get very well supported by textbooks. I feel like there's a few places within the physics community, specifically in the way that we teach different concepts. I think that there's some things that we teach that are, at best they're misleading, and in some ways they're just wrong. But we've just kind of gotten into that habit, and I feel like it's important to get over that and think in terms of what's really going on. Okay, let's get back to that integration. The integration was coming along pretty well here. The r squared's canceled. We said that's a big effect. And then what we're left with is a sine to the 3rd power theta d theta from 0 to pi. Now we could stop and go through this kind of step by step. I'm guessing from like Math 3b, you probably know how to do that integration. That integral, you can rewrite the sine squared as 1 minus the cosine squared, and then you can define sine theta d theta as the derivative of they're like these techniques using sines and cosine functions, and that's kind of a not too difficult to medium difficult sort of problem. Anyway, I did do the integration, and when I carried out the integration, I got a factor of 4/3. So that is going to include a factor of 4/3 into our formula. We're ready. This is the big finale as far as this derivation that we just went through. So our power formula says that the total amount of energy being radiated by an accelerating charge depends on, well, it depends on the electromagnetic force constant. It depends on how much charge we've got that is undergoing the acceleration, and it depends on how much charge squared. It depends on the acceleration of the charge, that also gets squared. And then I got to go in and divide through by c to the third power. And then I got this factor of 4/3, sorry. I really wanted to be down here. So when I take the 1/3 and the 4/3, that leaves me with 2/3. And then you can see everything else. So again, you know, kind of the big message here is that this does not drop off, and that means that there's a net energy transfer away from the charge, and that's going to end up, there's a radiation effect that takes place when these charges are accelerating. Okay? Now again, this is not a derivation that you guys are responsible for the midterm or for the final. So I know we're getting really close to that, so these more difficult examples that we're looking at, they're just for fun right now. So focus on, again, if you look at the homework problems, for example, the homework problems will give you a good idea of what sort of calculations you want to be able to do. All right, so let's do a couple more examples. Now, I'm thinking this actually is an example that you would want to be able to do. This is how much energy is there calculate the values. I've got it. Calculate the values of electric and magnetic fields for sunlight. Now, the value they gave us for sunlight here, 1,350 watts per square meter. That's not at the surface. That's actually above the atmosphere. So I kind of wish they would have given us a value for how much reaches the surface. But in any case, not so important. This is the intensity of the light, 1,350 watts per square meter. And we want to find out what are the values of the electric field and the magnetic field of the light coming in to the Earth from the sun. So let's take a look at that. So here's the energy in sunlight, and we're going to start off with their 1,350 watts per square meter. They are calling this S, or pointing vector, but we're just going to call it intensity, because that's what it's been in every other chapter in the book. So here's an intensity of light, and that's what's given in the problem. And then we can just step through the formulas that we just outlined. So what I can do is I can come up with an energy density by taking the intensity and dividing through by C. Now I've put little subscripts, average subscripts on this to remind us that we're really looking at average values of intensity. You know, if we have electric and magnetic fields that are varying from one location to the next, then we have to find a way to average over those effects. And so that's what the averaging is going to do for us. By using an average in the intensity and the energy densities, that means by the time we get to the fields, those are going to be in RMS values. So we've seen this before, peak versus RMS, factors of square root of 2, and then average versus peak, factors of 2. So I've calculated the energy density of the sunlight coming in, and that's coming in as 4.50 microjoules per cubic meter. And again, you know, you're going, really, it's a nice sunny day. Isn't there more energy in the sunlight than this? But there's not much in each cubic meter. Now, on the other hand, the sunlight comes in really fast. So there may not be much in each cubic meter, but if every second think of the speed of light. If every second you've got 300 million of those cubic meters coming in and hitting the surface, then it becomes a lot of energy. Okay, so this is pretty sizable, and you can run a set of solar panels from that and generate a good amount of electricity from those solar panels. Let's see. So the total energy density was 4.50. We're going to now divide that out, do a little bookkeeping here. We're going to assign half of that to the electric fields, and we're going to assign half of that to the magnetic field components. So we're going to divide up that energy density into 2.25 microjoules per cubic meter. And then finally, we can use our field formulas, our energy density field formulas, this time solving for the fields. Before we did it the other way around. We started with the fields, did a series of steps, step from the fields back to the intensity. In this example, we're starting with the intensity and working our way back through the field calculations. So the sunlight's coming in as having 713 newtons per coulomb is the value we get for the electric field. And we know that C times B is going to be the very same. So E RMS and CB RMS are this 713 newtons per coulomb value. And then to convert that into Tesla, we divide through by C, and we're getting 2.38 microtesla for the magnetic field. All right, there's an additional calculation we could do here. And so I thought, let's go ahead and introduce it right now. And the question is, hey, if I've got sunlight coming in, and I have a surface, and the sunlight comes in and it's completely absorbed. Let's say that the sunlight is completely absorbed by this surface. Is that going to exert a force? And the answer is yes. And the reason is that photons, the particles of light coming in, have momentum. It's not MV momentum, like for objects back in Physics 4a, but there is a momentum. So based on how much energy the photons have, they also have a certain amount of momentum. And the formula for that is that the momentum of a photon of light, the momentum of an individual photon is equal to the energy of that photon divided through by C. So that allows us to calculate how much momentum. And if you remember, forces can be written in terms of the rate at which momentum is transferred into something. So if objects run into each other, the force acting between the objects depends on how much momentum is being transferred, and specifically the rate at which momentum is being transferred. So if I shine light on a surface and I just leave that light turned on, there's a certain rate at which momentum is being transferred into that surface. And that will tell me how much force is being exerted on the surface. Now, we've set this up as if the light is being perfectly absorbed. What happens if it's perfectly reflected? So if I have light come in, but the light bounces off the surface and reflects back out, that doubles the effect. That will give me 2 times as much force because, well, I guess the argument mathematically is momentum in this direction is not the same as momentum in the other direction. In order to have something hit and bounce back, first of all, it has to transfer all of its momentum, and then we have to transfer even more momentum back in to get it to come back off in the opposite direction. So if it's coming off in the opposite direction with the same amount of momentum, but 2 different directions, then the amount of force is doubled. So we've got this set up as a perfectly absorbing system. We've got another example we're going to take a look at where it's perfectly reflective. And in the perfectly reflective example, we got to remember to put an extra factor of 2 in. So here's what the formulas look like. The force is dP dt, and P is equal to U over C. So the force can be calculated as 1 over C du dt. Now, d energy dt is power. And so I just wrote that out. 1 over C times power. I didn't want to get it mixed up with pressure. You know, we're looking at forces, and there's also formulas for calculating pressure. I wanted to make sure we were looking at power. Power is equal to intensity times the area. So I thought, perfect. What if we have a building, and we take a look at the cross-sectional area of the roof, and I've got sunlight coming right down directly on the roof of this building. How much force will that exert? So I figured, okay, you know, maybe my house roof is like 8 meters by 12 meters. It's about 100 square meters roughly. So let's say that we have a house, and it's got a roof, and it's like 100 square meters. Now, I don't live close enough to the equator. There is never a time during the year when the sunlight is directly coming down onto the, we could angle the roof. In any case, let's imagine the sunlight's coming in very directly, hitting that roof. Well, I've got an area of 100 square meters. Uh-oh, the square got dropped. Add that in. And then the power is going to come from taking the intensity and multiplying by the area. So for this, I went back and used this intensity. Now I know this is the intensity above the atmosphere, not the one down at the surface. Sorry, I should have used a lower value. But I went ahead and used this 1350, and then I multiplied it by the surface area, and it said, hey, the total power of sunlight hitting my roof, it's like 135 kilowatts. That's an enormous amount of energy. That's more than enough to power all of the energy needs of the home. Now, solar panels are only like, I don't know, 10% efficient or something, so they're not going to be able to collect all of that. But even at 10%, you're looking at 13, 14 kilowatts, which is a pretty good power rate if you cover the whole roof. I guess you got to cover the whole roof too with those solar panels. So my solar panel system, which recently went in, on a good day, brings in 7.4 kilowatts. So anyway, it doesn't cover the whole roof, but it covers as much as was practical. Let's see. So we've got the power calculated, and now that we got the power calculated, we can calculate the force. I can take the power, divide through by C, and it says, look, that is the force of sunlight beating down on my roof. It's like 450 micronewtons. That's nothing. So I don't think it's going to collapse the house. 450 millionths of a newton is not an extraordinary amount of force. It's pretty tiny. But it's a useful calculation, and anything like this too. I mean, this is something, you've got homework examples kind of like this. Definitely this is a good sort of example to take a good look at and understand. All right, this is the textbook or the slide producer's version of this, and you see this is kind of the same thing. They're calculating, this time they're doing pressure, They're doing force per area. Now it turns out that the pressure can be shown to be the intensity divided by C. So these are pressure calculations, not power. And then if it's fully reflected, that will double the pressure. So you can follow through these formulas too and see how they've come up with the pressure calculations. All right. Ooh, this was an interesting example. So this was an example that was included in these slides. I don't think it's in the book. Maybe it is, maybe not. Anyway, it says, let's imagine if sunlight can exert a force, why not build spacecraft that carries up a sail, and then it extends an enormous sail, and that sail actually has a force acting on it. So you turn the sail towards the sunlight comes, it hits the sail, and it propels your spacecraft. That seems like an idea. Let's see how practical that might be. Now, what they said was, we're going to build this solar sail, and proposals have been looked at. This has been going on for a long, long time. So 50, 60 years or more, people have been wondering about this. Now, there was an effort years ago, I remember, it's probably been 10 years or more, a spacecraft was built, and it was sent into orbit, and it was to extend a sail. I don't know if that was ever successful. I don't know if they ever got the sail fully extended in order to get enough force to kind of do measurements of whether solar sails would be practical. So what they're saying is, here's the size of the sail. It's going to be 1 square kilometer. So if you think of the sail as being, a kilometer in size by a kilometer, that's a pretty big sail. But, the bigger the sail, the more sunlight we can capture, and the more force we'll have available to propel our spacecraft. So it says the spacecraft is 5,000 kilograms, and what they're saying is, if the spacecraft starts from rest, how far could it go in a year? And I'm thinking, well, which direction are we talking about? And if what you're trying to do is send this spacecraft out of the solar system. So let's say that we're going to try and propel something out of the solar system or into the deep part of the solar system. What would happen to this spacecraft if it successfully could get its sail set up and get pushed out? Now, I'm assuming for this, you couldn't start from the ground. You'd have to have a traditional kind of rocket to boost this up away from the Earth. You'd want to get away from the Earth's gravitational effect. So you could take a rocket, boost it far, far away from the Earth. Wouldn't have to be terribly far until the Earth's gravity would be not significant. But then you'd have to deal with the sun. The sun would still be exerting gravity. Anyway, let's take a look at some of the numbers and see if this is a plausibility. So here it is, solar sail, maybe our last cool example for the semester. So anyway, here's the sun, here's where the Earth is, and we have launched this spacecraft away from Earth. It has unfurled its sails, and it has oriented them so that the sunlight will push it out of the solar system. Let's see what happens here. So I wrote down the given information. 5,000 kilograms, cross-sectional area, kilometer by a kilometer, that's 10 to the 6 square meters. The intensity of sunlight, at least near the Earth, is going to be 1350. Now, that's an issue we got to be a little concerned about, because it's 1150 watts per square meter here, but if we use this sail to travel to the outer part of the solar system, by the time we get to, say, Neptune or Pluto, Neptune is like 30 times farther than the sun than Earth is. And at a distance of 30 times the distance that Earth is, that's going to take that sunlight intensity, that's going to drop down to, well, it's like the distance squared. So that's going to drop off by a factor of 900. If we go out to Pluto, that's like 40 astronomical units. If we go out to Pluto, the intensity of sunlight is less than 1 watt per square meter. So if you've seen those pictures of what would the sun look like, sometimes they'll take spacecraft and point them back towards the sun when they get out to Jupiter, Saturn, Uranus, or Neptune. And oh my gosh, the sun's a little tiny thing. That was one of the best scenes, I thought. I recently saw the movie Ad Astra. It was okay. If you haven't seen it, it was okay. But one of the best scenes that I liked in there was they were out, I think, at the planet Neptune. And it was the planet Neptune. And they had a scene where they looked back, and there's kind of a really bright star off in the distance. And at first I thought, I wonder what star they want that to be. And then I realized that's the sun. So that was a nice moment. Nobody mentioned that was the sun. You just kind of had to figure that out, I guess. That really bright star in the distance, that's as bright as the sun would be in the sky if you were in the outer regions of the solar system. Anyway, so that's not going to be a constant as we move outward. So I did a quick check at the orbit of the Earth. How much force would there be on our sails due to sunlight? I plugged into the formula. Look, I put the factor of 2 in. I said it's a perfectly reflective surface, and so I'm going to get that extra factor of 2. The sails are real shiny. This was just a little disappointing. 9 newtons. That's it? 9 newtons of force? That's all I'm going to get from this sail that is a kilometer across and a kilometer this way? All right, so I thought, well, how much gravitational force do we have? I calculated the gravity on the spaceship based on 5,000 kilograms. Gravity is 30 newtons. So this sail all by itself is not going to take us out of the solar system. I think we need a bigger sail, right? So the conclusion here was, here's my force diagram. I got the force of sunlight. I got gravity holding me back. And I'm going to need a bigger sail. So I made the sail 100 times bigger. So I made the sail 10 kilometers by 10 kilometers. And why not? We'll just get a really big sail. And when I boosted the size of the sail and made it 10 kilometers by 10 kilometers, now I have 900 newtons. And that 900 newtons is much bigger than the 30 newtons due to gravity. I'm looking pretty good now. So my net force then is 870 newtons. Now, 870 newtons is not much of a force for a 5,000 kilogram ship. It's only going to provide me, at least initially, it's going to provide an acceleration of 0.174. Now, the advantage with the sail is that I am consistently going to be pushed by the sunlight during the entire trip. Think about this. If you're launching a traditional spacecraft where you turn on the rocket boosters, how long do the rocket boosters stay on? 5, 10, 15 minutes, and that's it. That's all you've got to work from. But with this solar sail, the solar sail is going to be up the whole trip. Unless it tears. I hope nothing happens to the sail. So even though it's a tiny acceleration, as long as we're patient, that tiny acceleration will gradually build up our speed. Now the downside is, what we mentioned, is once we get out into the solar system, the force is going to drop off. It's not going to be as large, and we won't have as large of an acceleration. But we will keep picking up speed the entire trip. So that's what we're counting on. So at least initially, we're going to start off with 870 newtons, and then it's going to drop off. Now in the problem, what they asked us to do was to say what's going to happen after a year, and that actually is a difficult problem. So I chose not to go through that. That involves finding velocities and then carrying out integrations of difficult functions. And I think we get lost, and I'm not that interested in looking at all the details. So what I did instead was I said, let's imagine we want to sail out to Pluto. Earth is at a distance from the sun, 150 million kilometers, and Pluto is about 40 times farther. So what we're going to do is find out how much energy am I going to get due to the force of sunlight. So I'm going to say there's a work that we're calculating, an energy transfer, and the energy that I'm getting from the sunlight, the accumulated energy, will come from integrating the force over the displacement as we sail out of the solar system. So I'm going to integrate from where the Earth is located out to where Pluto is located. And remember, that's 40 times r. Now, the force is going to drop off. And so I wrote in the initial force, which we calculated on the previous page. I think it was 870 newtons. And then I put in a factor of r squared over little r squared. And that's because the force is going to drop off like r squared. In fact, both forces, the sunlight drops off like r squared, and gravity drops off like r squared. And that means I can use that 870 number, I can include gravity in my calculations, and just write it as big R squared over R squared, and that'll tell me how the force drops off. When I'm right where the Earth is located, the force is F naught, but as I head away, the force will drop off like 1 over R squared. So I carried out the calculations, and what I found was, by the time we have sailed to Pluto, sunlight will have provided 1.30 10 to the 14th joules. So again, the sunlight's just shining all the time. And so I'm constantly getting a push. Now, unlike traditional rockets that we bring up to a big speed and then we turn off the engines and they slow down as they leave the solar system, our sail spacecraft is going to pick up speed the whole way. Little by little, it's going to start off going pretty slow, and then it's going to gradually pick up speed. So I took all of that energy, the work that was done by sunlight, and I said it's all going to become kinetic energy. So all of the work, all the energy that was transferred in, is going to show up as kinetic energy, and that's 1.30 10 to the 14th joules. I solved for the speed based on the kinetic energy and mass, and look, by the time we get to Pluto, we are going 230,000 meters per second. That's pretty impressive. So how fast are traditional spacecraft going by the time they leave the solar system? And I'm not sure. I'd have to look that up. But they have slowed down most of the way. But this is just picking up speed. Now, I think we can see from this calculation right here, as I go farther and farther out, I'm not going to pick up there's a maximum amount of energy that I can pick up. So I can kind of ignore this 1 over 40 effect and say F naught times R, that's kind of the total amount of energy that I will ever integrate by this sail based on sunlight. So the number we've got in terms of energy is not going to go up significantly, and the speed at which the spacecraft is going to be traveling, that's kind of its maxed out speed. Its maxed out speed is going to be 230,000 meters per second. Wow, that's pretty fast. So, you could imagine, well, how many years might it be, or decades, or hundreds of years, to get to a nearby star. Now, I did estimate this. I went back and I'm estimating that this process would take months. So if we start off at rest in Earth's orbit, it's going to take like months to get the spacecraft out to Pluto, but that's not bad. The spacecraft that we have sent out to Pluto took, what was it, 10, 12 years, something like that. So this actually seems pretty fast. We do have to build those enormous sails and make sure that they're durable. They don't have to withstand much force. The forces we've looked at are pretty modest. Less than 1,000 newtons. So it's not an incredibly large force, but the sail is really spread out to capture the sunlight, and that might make it fragile. Anyway, kind of a fun problem, I thought, to wrap up the semester. Okay, let's kind of finish out the end of the chapter. Again, some of these sections at the end, don't worry about these so much. Don't worry about the solar sail problem. Let's go back and see. So on this problem, you should be able to calculate the force of sunlight, and I guess that's about it. You should be able to calculate the accelerations too. So if you knew the force of sunlight, on a good day you should be able to calculate gravitational forces. You should be able to do kind of the first page of this, I guess. Second page was a little trickier, but even that doesn't look too bad. So, you know, you could look at it, see if that makes sense. There's some of these later sections. These are just kind of descriptive. They're just giving us some background information about how these electromagnetic fields are used to communicate. I'm not going to spend a lot of time, but it says here is someone speaking into a microphone. There's sound. Sound is being converted by kind of those magnetic effects, those induced currents that we looked at in chapter 29 or 30. And so that's going to become, there's an amplifier to generate the signal. And then what we're going to do is we're going to take the voice signal and mix it. This is where the frequency of the radio station comes in. So I've got this signal going on from the microphone. It's got its own set of frequencies. But what we're going to do is combine that. We're going to modulate this radio frequency oscillator. And so that's what we're going to send out. We're going to send out what is mostly the frequency of the radio station with some little variations in it, and the little variations are the information about the sound that we want to transmit. All right, so if we have a carrier signal, now the carrier signal for AM is a perfectly, well, for AM and FM, the carrier is a perfectly uniform frequency, but then here is this audio variation, and so what we do in FAM is we modulate the amplitude. AM stands for amplitude modulation. So we take a uniform amplitude carrier signal and we merge that with the audio that we want to encode, and we encode it as a variation in modulation. For FM signals, again, we start with a perfectly uniform frequency, perfectly uniform amplitude carrier signal, and then this time, wherever there's a rise or fall in the audio, we vary the frequency a little bit. So I don't know if they did that, I don't know if they scaled that exactly right. So we're showing that wherever the audio intensity picks up, we increase the frequency a bit and then we drop back down and we increase the frequency. So these slight increases in frequency, that's the signal that's been embedded into the carrier signal, and that's what gets transferred. So FM is frequency modulation. And at the other end, the radio picks up, there's the receiver antenna, and it undoes the modulating and sends the signal to a speaker. So, and the speaker vibrates with the same pattern that the original person spoke with into the microphone. This is saying that here's the antenna, this is a ground. So here's an antenna picking up a signal, and we looked at this. We saw that by using a combination of inductance and capacitance, that we can select a particular frequency, so that only the signal from one radio station continues on through the signal and gets amplified in a radio and TV wireless communication. Here they're just looking at different shaped antennas. So with a vertical antenna, we said that the electric field then is going to be limited to vertical polarizations. We can use different shaped antennas to pick up different portions of the signal. Here they're saying that along with the magnetic field that's coming in, as the magnetic field comes in, it's going to set up currents in a loop antenna, so we can use the magnetic field components as well as the electric field components by picking a different shaped antenna. All right, here's Maxwell's equations. Again, they're going to claim these are the basic equations of electromagnetism. I am going to disagree. I'm going to say the direct approach is more intuitive, it's easier, it's easier to see what's going on. But it is true that in situations we want to be able to come back and use the Maxwell equations to be able to solve for electric and magnetic fields. And now this is a little hilarious, I guess. I noticed that in the summary of chapter 31, all through the chapter they've been saying oscillating electric fields generate magnetic fields, and oscillating magnetic fields generate electric fields. Did I say that the same? Anyway, they're saying that the fields generate each other, and I've been crossing it out with a red marker. Look what they put in the summary. Electromagnetic waves are produced by accelerating charges. Yes! All right. Had to wait for the summary for that. And it says that the propagation speed is given by c, and it is not a derivation from this. It is a fundamental constant of how space and time are configured in nature. So c is c regardless of what these other things are. Let's see, the fields are perpendicular, E and B are perpendicular, and mutually perpendicular with the direction of travel. The speed, the wavelength, and the frequency are related by that formula. It's a relational formula, not a causal formula. All right? So, but it works. So we need to calculate that. When we get down to intensity, they are calling it the pointing vector, and they're giving it a symbol S, but it's really intensity. Now here, again, they've gone back and written it in terms of mu naught, which you're welcome to use if it makes sense, but you've got to find your own way through with that. I'm going to recommend using little k instead of mu naught or epsilon naught, so we can stick with one force constant. So work in terms of little k and c is my recommendation. If you want to take a shot at epsilon naught and mu naught, that's fine too. That is your decision. All right, so celebration here at the end, when they say in their summary, electromagnetic fields, propagating electromagnetic fields are generated by accelerating charges. All right, that kind of wraps up the semester. So we got a midterm, we got a final coming up. There'll be review, sets of review problems. I'm sure you're looking through all your homework problems, so hope everybody has stayed caught up through all of these weeks.